Good afternoon, everybody. It's my pleasure to introduce Khulekani Khumalo, otherwise known as KK, to all of us as our speaker today. KK has been at Wits his entire time. Started in 2014, completed honors in 2018, and then started his MSc in 2019, and then converted to a PhD in 2020 with me and Lou. And he submitted his PhD in December, and just at lunchtime today we found out it's been accepted with minor corrections. So congratulations to Dr. Khumalo, and I will hand over to KK to give today's talk.
Hello everyone, I'm KK, Khulekani Khumalo. So today I'll be presenting my study on Ventersdorp supergroup. So the study is about constraining the mantle sources of the Ventersdorp supergroup, as well look at the PGE concentrations of the supergroup. But the title of this talk is the magma sources and the PGE potential of the Ventersdorp large igneous province. I'm being supervised by Prof. Lou Ashwal and Dr. Hayes.
Just get a laser pointer for you.
Okay, just a background on the large igneous provinces. So these are large volumes of magmas that are emplaced on cratons or into the cratons in a short period, usually less than 5 million years. Some can go up to 10 million years. And they can be emplaced on continents, and those will be the continental flat basalts, such as the Ventersdorp that was emplaced on the Gulf Craton. There can also be occurs intrusions, such as the Bushveld complex here in South Africa. Some are emplaced on oceanic plates, such as Otong Java Plateau, seal complexes, as well as black swans. There are other people who have compiled these large igneous provinces globally, and they've published books. And you can search them and find them if you like, or buy them. And the sources that have been proposed for the large igneous provinces include the sublithospheric mantle. Other people go further and say it's a mantle plume. Other people have proposed the subcontinental lithospheric mantle, the SCLM. Or other people have proposed that there could be some enriched zones within the SCLM, the depleted SCLM, that can still produce these large volumes of magmas. And other people propose the convecting mantle, the asthenosphere mantle. And here I've taken some snapshots of titles from journals. This one looks into the hypothesis of mantle plumes, whereas Prof. Lou published a paper looking into the 4 overlapping large igneous provinces here in Southern Africa, including the Ventersdorp, where he proposes the sublithospheric mantle sources. Some people have looked into Umkhondo LIP, which is being analyzed, studied by Dr. Ben Hayes. And also, there's a paper here that is looking into the SCLM. Again, there's also a website that you guys can visit if you like to follow this subject. This is the largeigneousprovince.org. So they usually have the LIP of month and also discussions in that website. And there are other people who have also studied or looked into the plumes as to see if are there viable models to explain these large igneous provinces. So on Ventersdorp supergroup, this is a neo-Archean sequence about generally 2.7. However, we're going to look into that, into the age of this supergroup. It comprises volcanic and sedimentary rocks that have been metamorphosed to green schist. So it is subdivided into the basal Klip-Riefersberg group. That is the VCR, the Ventersdorp or the Ventersdorp contact reef, where it overlies the Witwatersrand supergroup. And there's also the Plattberg group, which is mostly felsic. And then the uppermost group or sequence is the Nile sequence. That is the Allen Ridge lavas and the Botterville sediments. And the whole supergroup is overlain by the Transvaal supergroup. So on this map, there is the Ventersdorp, there's the Witwatersrand supergroup, and I've even shown the Transvaal supergroup. So for the Ventersdorp, it is exposed in a northeast-southwest trend elliptical area. These are the metrics. So so the dark green that you see here corresponds to the Klip-Riefersberg sequence. The yellow corresponds to the Plattberg, and the greenish brown is the Nile sequence. And okay, so looking at this, the exposure on the surface, you wouldn't say it's a large igneous province. However, there are people who have drilled and they've intercepted the Ventersdorp, such as here where the Dexter, this is where the samples come from, and the samples are not collected by me. They were collected by students of Professor McCarthy. So this background green here, this is the subsurface extent that we think the Ventersdorp covers, almost the cover craton. This is based on bore data, geophysical data, because they've also, using geophysical methods, they've also identified Ventersdorp in the western portion of the cover. So the qualities of the Ventersdorp on the cover craton. Initially, the Ventersdorp was described in the area of Botterville during the exploration of gold, Wits gold. However, when they started extending outwards, they came across similar sequences that they correlated to the Ventersdorp around the area of Tau, Freiberg. And there are others that correspond to the Klip-Riefersberg, this dark green or the green exposed rocks here in Botswana and the western portion of the Gauval. So those are the qualities of the Ventersdorp on the Gauval craton in the Pietersburg block and the Wits block. And the other people have also correlated the Ventersdorp supergroup to the Fortescue group on the Pilbara in Australia. So this is a map from Gumsley 2017. So this map is the Pilbara craton, and this side we have the Gauval craton. So the blue corresponds is the on this map is the Fortescue group, whereas on the Gauval is the Ventersdorp. So this correlation has prompted a concept that there was a supercraton during the formation of the Ventersdorp supergroup that they've termed the Valbara supercraton. And some have also identified similar sequences that is similar to the Transvaal sequence on the Pilbara. This is a summary of the equivalence of the Ventersdorp both on the Calvara and as well on the Pilbara. We have the sodium group, the Zoutleaf group, the Daum formations, and the Amelia group. And this is the Pilbara Fortescue group in Australia. And here I did not include the equivalents of the clip refer spec here on Calval, the ones that are located or situated in Botswana. So right now I'm going to go into the Western Royal Comatiates, which is part of the clip refer spec group. So just on comatiates, these are high magnesium rocks that have greater than 18 weight percentage of magnesium oxide. They are almost restricted to the Archean. However, you do have some occurrences later. And you see that they were being extruded or placed at high temperatures. And just towards the end of the Archean or at the end of the Archean, you see that they disappear. And this has brought in some debates about the dynamics of the mantle, whether the mantle was circular cooling of the mantle, or was there any chemical evolution of the mantle? And was there any change in the style of subduction, the rate of subduction for the comatiates to start disappearing? And with the comatiates, you have types of comatiates. You have the aluminum depleted comatiates, the aluminum enriched comatiates, and the aluminum undepleted comatiates. And also there's the fourth one, which is the titanium enriched comatiate. So the Western Royal comatiates, as I said earlier, that they occur in the clip refer spec group of the Ventersdorp at the base, just overlying the VCR. So the VCR, or its equivalent of the VCR, has been dated to be about 2.78. And the R18 was initially dated by Armstrong in 1991 to be 2.71. However, this date has been revised to about 2.78. So we can bracket the Western Royal to be about 2789 to 2764. And where they've intercepted the Western area, they have seen that it is at least 50 meters thick. And the samples that are analyzed go up to 25 weight percentage of magnesium oxide. And what we also notice is that these Western Royal comatiates have higher titanium oxide compared to the typical comatiates that we know. One of the issues that we came across is that the supergroup has been metamorphosed as well, altered. So that was one of the challenges that we faced in the study. Here, looking at the petrography of these comatiates, you see euhedral forms of what you can say it used to be olivine, with some resorption texture there, features, using the transmitted light microscope. And within this flow, you find these phenocryst-rich pockets that are within a ground mass or matrix. And when we analyze these samples in sections using TIMA, we see that the matrix is actinolite rich, and the phenocrysts that we identified have been chloritized. And we do have some silica rich that were identified as quartz. Okay, this slide shows evidence for hydrothermal alteration. There's a vein going through that comatiate flow, a calcite, and a quartz vein. And you can see that the occurrence of quartz fades away from the vein. And here you can also see the preferred or the alignment of the phenocryst in the flow. Yeah, there's a slide missing. Yeah. And then further, we see the chloritized olivine. But however, in other areas in this porphyritic zone, the olivine was not clarified, however it was silicified. Because when you put it in timber, it is identified as quartz. As we can see from the form or the shape of the crystals, is that it resembles the olivine. And you also have the spinifex zones within the floor. The needles have been also altered to actinolite. Surprisingly, and also we're lucky to identify fresh cyanopyroxenes within this floor. As you can see here, there's cyanopyroxene phenocryst within the spinifex zones, and also we have a cyanopyroxene cumulate zone. So we probed these cyanopyroxene using EPMA. This was done by CPSHF and Sarah. And you see the composition of this CPX dioxide. Okay, so moving on to the major element chemistry. So the major element chemistry data was not done by me. This I collected from the literature. This was done by the students of Prof. McCarthy, Myers, and others. You can see that our rocks, the samples classify as komatiites. Well, also here they indicate that they are aluminum depleted. So I've put in Barbertine komatiites as a reference for depleted and undepleted komatiites. On the side, this is our data that we produced, new trace element data. We see that these, the Western rare komatiites are enriched in light rare earth elements over the heavy rare earth elements. And the red and the blue one are the samples that deviate from the norm or from the rest of the group. And with the multi-element diagram, we see that the mobile elements such as rubidium, barium, strontium, they show these anomalies. However, also identify titanium negative anomalies. And there's some samples that are showing a negative niobium and tantalum. And we also analyze these rocks for strontium, neodymium, hafnium, for rock data. And for the oxygen, this was in situ for the cyanopyroxene. This was done here at Wits using the Wiggle separation methods, where we separate the neodymium from the rest, and then the strontium and the hafnium. These are the results. However, looking at this strontium, you see that it's wide. It ranges, which could be due to the alteration that we have seen. However, with the epsilon neodymium or neodymium and hafnium isotopes, they don't show a similar spread of the data, such as the strontium. The epsilon neodymium ranges from -1 to +2. The hafnium ranges from -1.7 to +3. Okay, from this, you can just say that the source was of depleted mantle composition. One thing on this plot, you have epsilon, hafnium, and neodymium, is that here you can see two groupings, this group here and this one, and these two samples. The difference between these two groups is that these samples have come from a different borehole that showed more alteration compared to this borehole, where we took most of our samples from. So that's the whole rock data for strontium, neodymium, and hafnium isotopic compositions. And then for the in situ oxygen isotopes, we have the delta 18 here, And you see that we had 49 spots that were analyzed that range from +4 to +5, which is the normal mantle composition. And on this plot, we've also plotted the range for SLM. We also plotted the range for the bulk mantle and also the mantle CPX. And we see that our samples fall within the mantle CPX range, very restricted, there's no spread of data. So to constrain the composition of the source, I've presented that there's alteration, and we see that the strontium isotope was altered, so it cannot be of use to constrain the source. However, we also noticed that there was some fresh CPX within the samples that we were able to probe for oxygen isotopes. And we also know from literature that the hafnium and uranium are more robust compared to strontium, especially the hafnium system. And we see with the hafnium that we get the depleted mantle signatures. However, we're not able to use these systems to model contamination because we don't have data for the contaminants or possible contaminants for these magmas. And also, we also saw the light, the enrichment of light rare earth elements over the heavy, which is not what we expect of typical komatiites. The question is, we see alteration. Is this enrichment due to alteration or mobile or fluids that were passing through these sequences that enrich the rocks in the rare earth elements? And one possible explanation will be carbonic fluids that are percolating from the Transvaal, that those fluids can form RE complexes, and they could have influenced the Ventersdorp lavas. However, with the isotope, with the oxygen isotope composition, we also test the alteration and contamination. So this group, these 3 samples here, are from literature as well as these yellow samples here. This was done by Harris and Watkins in 1990. So the yellow samples here represent the Wits quartzite that are associated, that are close to, adjacent to the Ventersdorp or the Klip-Rufusbeck sequence. And these 3 samples, this is the samples from Conera Sill that have been linked to the Klip-Rufusbeck sequence. And we see that this Conera Sill, which represents the Klip-Rufusbeck sequence, does coincide or has similar composition as the CPX that we analyzed within the Western area samples. And also knowing that within our samples, it was altered, there was fluid passing through. However, we can be confident that the oxygen isotopes that we analyzed were not altered to a point where we cannot say anything about the source. So we're confident that we are observing a mantle composition signature. And also, if there was any contamination that might have influenced this phenocryst, or any fluid that passed through the Wits or the Transvaal and affected the Ventersdorp, we'll see a deviation of the composition from what we're observing. So just to let you guys know is that the average that we analyzed for the delta 18 was +5.28. which is again falls within the mantle composition. So we go and look at the Ventersdorp supergroup, the whole supergroup. Before we do that, I'm just gonna give you a background on the supergroup again. We have the clip reverse back group at the base, the blood bag, and the null sequence. Initially, this whole sequence supergroup was thought to be 2.714. However, now they're starting to redefine the Ventersdorp supergroup, with more dates being published and more analysis being done on these rocks. And our study does contribute to those debates. So, Gamsley in 2020 published saying that the clip reverse back is 2.78, the blood bag is 2.72, and there are other people who have published similar dates before, such as Cornell et al. 2017. And then the null sequence has been dated to be 2.68. And there are also other dikes, Rycopy dikes in the eastern section of the Galval that have been linked to the Alden Ridge sequence. And they're also 2.68. Okay, classifying these groups. On this plot, you can see that I used elements that are less susceptible to mobilization, such as zirconium, zircon. With the clip reverse back group, we see that it is different from the blood bag group. With the clip reverse back group, you see this horizontal array that classifies all salts. And then whereas with the blood bag group, you see that it's more felsic and acidic in composition. And however, the Nile sequence, the Allen Ridge, represented as the yellow squares here, are more similar or close to the clip reverse back lavas, especially the Albertine lavas. And on this diagram, the AFM, we see that the western area are more chromatic, whereas the rest of the clip reverse back is doylitic and with some affinity of alkaline. And the blood bag or the Nile sequence here is more alkaline compared to the clip reverse back. And this data is from literature. We did not produce this data. And okay, on these plots, I'm gonna first refer you guys to the inset plots, where you can clearly see the differences between the clip reverse back group, shown as green, the blood bag group, shown as red, and the Nile sequence, the Allen Ridge, shown as the yellow squares. And the other thing that you will see within the clip reverse back is that the western area comets cluster away from the rest of the basalts of the clip reverse back. On this plot, you can see that the western area comets have higher silica content than typical comets. And earlier on, we saw that there was evidence of veining, quartz vein. And on this plot, you see that the western area plotted higher titanium, whereas Barbertine comets will plot in this region. So they do have higher titanium compared to the typical cometiates. Okay, with this rare earth elements, profiles, or patterns, this one I've plotted the whole Ventersdorp sequence. You can see that this is the clip reverse back sequence, and I've plotted the blood bag sequence here. And moving into the Klippersberg group. In the background, the green background, that's the western area that I presented earlier. We see that there's a spread of the light ray earth element where the western area overlaps with the rest of the Klippersberg sequence. However, you see some differences, some slight differences within the heavy ray earth elements. This again could also say something about alteration of the western area comatites. And here I've plotted the Klippersberg without the western area comatites, where we see that there is still that spread that I described earlier of the light earth elements, whereas the heavy, they seem to be in a tight range or narrow range. And I've also plotted the Allen Ridge lavas. And you can see here the overlap with the Albertine represented as the blue. And throughout the study, we see that the Allen Ridge has similar composition as the Albertine. And also here, what you will notice is that the sequence of the Klippersberg is the western area at the base, overlain by the Albertine, Orkney, Janet, and Lauren Edenville. And on these profiles, you will see that the Albertine that overlays the comatites is more enriched compared to the uppermost unit of the Klippersberg, which is the Lauren Edenville picrites. And on this plot, I've plotted the Flatback sequence represented as the gray triangles and the red triangles. And I've also plotted the Allen Ridge lavas, the yellow squares here. And we see that the Allen Ridge, which overlies the Flatback, is less enriched compared to the Flatback group. And I've also plotted the multi-element diagram here, and I've also included the western area as represented by the green area here. And what we notice is the differences in the strength of the negative niobium tantalum anomalies. They were not so evident in the western area comatites compared to the rest of the Klippersberg. And we see that the effect of the alteration is different between the two groups on the mobile elements. However, we see similar titanium negative anomalies. And one more thing that we noticed that the western area shows negative strontium, whereas the rest is positive strontium anomalies. This is for the Klippersberg. And below that plot, we have the Flatback sequence as well as the Allen Ridge lavas. And we see that they also show the negative niobium tantalum anomalies, also stronger titanium anomalies. This is the strontium, neodymium, hafnium data. I'll first look into the strontium. Like I said earlier on, is that there is a spread of strontium data, which we don't trust. We have attributed that to the alteration and also knowing the rubidium strontium system that it can be altered by this low-grade metamorphism or alterations. However, with plotting epsilon neodymium and against epsilon hafnium, we see that the western area and the Klippersberg group, they do group together, with the comatites having the most depleted compositions. And the Klippersberg groups clusters away from the more felsic sequences, which is the Bloodback group and the Allen Ridge group. And what you guys notice is that the Allen Ridge lavas that have been showing similar composition to the R18, they don't have similar compositions, isotopic compositions. This grouping, or this group, the Allen Ridge and the Bloodback, they plot close to the crustal compositions, whereas the Clip-Rufus-Beck plot close to the mantle composition. Here I've plotted Epstein Hafnium against strontium ratios, and we still see that spread that we noticed earlier. So to talk about the Ventersdorp magmatic events and also accepting the dates that have been published, the Clip-Rufus-Beck group has been classified as its own large igneous province. So instead of having the whole Ventersdorp supergroup, now you have the Clip-Rufus-Beck large igneous province, which is about 2 kilometers thick. And also they've classified the Allen Ridge of the Nile sequence as its own large igneous province. And in this study, I propose that the Bloodback group is also a large igneous, looking at its thickness as well as the extent, areal extent. Strictly speaking, the large igneous provinces are defined on the basis of basaltic composition. However, the Bloodback is more felsic. Reading further on the large igneous provinces, there is another subclass of large igneous provinces that is termed silicic large igneous province. So in this study, we're going to refer the Bloodback group as the Bloodback silicic large igneous province. So redefining the whole Ventersdorp supergroup, you have the Bloodback lip at the base, you have the Bloodback silicic lip in the middle, and you have the Allen Ridge lip at the top. So these are the dates that have been published for these groups. You can see that the Clip-Rufus-Beck has dates around 2.78, together with its equivalents. The Bloodback has dates around 2.72, and then the Nile sequence has dates around 2.7 to 2.66. So the Ventersdorp magmatism, now we know that we have different, one more thing also here is that to show that these are different occurrences or magmatic events is that they are separated by unconformities. So between the Bloodback and the Clip-Rufus, there's an unconformity as well between the Bloodback and the Nile. So it was not one emplacement. However, there was 3. So we've established that this source was depleted. It was a depleted mantle source. And there's also these negative niobium in tantalum that we have observed. And these are normally attributed to subduction or subducted components that influence magmas. And plotting our samples on this plot is that you see that you show different influences between the Westonoria comatiates that show influence by the convecting mantle to the asthenosphere, compared to the rest of the Clip-Rufus-Beck that shows some influence by subduction components. So you see that the source was modified or interacted with zones that have been influenced by subduction earlier on, after the Westonoria was emplaced or formed. or the source was directly influenced by a subducted slab. And also looking into the Bloodbag slip and the Allen Ridge lip, we measured and reached isotopic signatures, and they also had negative niobium anomalies. And on this plot, we see a typical continental flat basalt composition that where most CFBs plot over this mantle array, indicating a magma crust interaction. And we see that with the most of our samples, they do indicate some of that interaction. However, with Western area, you see a minimum interaction. And we saw that with the CPX that we analyzed for oxygen isotopes, that there was no evidence. We could not prove contamination of these lavas for the Western area comatiites. So we can say there was insignificant contamination of the magmas during their ascent. And earlier on, I introduced the Valpara supergroup or supercraton. And we took the available literature data on the Fortescue group compared to what we have analyzed here, and also what has been published for the Western for the Ventersdorp supergroup. So what we noticed is that the Fortescue group from its base, which is equivalent to the clip reverse back on the Gaval, has similar composition as the overlying sequences that are equivalent to the Bloodbag and the Nile sequence. So these green circles here are Montreux basalts on the Pilbara craton, and these solid, the green circles here are the clip reverse back on the Gaval craton. And we see that they're different. The compositions are different at 2.78. However, going to the Bloodbag group and its equivalent on the Pilbara, they have similar composition. Same thing with the Allen Ridge lavas. And there are also comatiites on the Pilbara, on the Fortescue group, the Paradis comatiites, and those ones, based on the dates that have been published, they are dated to be 2.72. So that's why I put them here. And you see that they also have depleted mantle compositions, which are similar to the Western area comatiites or the clip reverse back basalts that we analyzed. But based on this, our data, neodymium data, does not support the existence of Valpara during the formation of the clip reverse back sequence. Maybe you can say something about the Bloodbag and the Allen Ridge formation. Yeah, so that's it for the Western, for the whole Ventersdorp supergroup. And I'll move into the platinum group elements. So the large igneous provinces, they bring lots of energy as well as ore metals that can form primary or secondary ore deposits. And these deposits can be hosted by the lips themselves. Just an example would be the Bushveld, or the ore deposits, or the minerals can be concentrated by the lips as they get emplaced. They bring heat, driving hydrothermal systems that can drive metals and get to concentrate those metals and form ore deposits. or they can form a structural fronts where the metals can concentrate. Another way of forming the ore deposits is weathering of the lips that can later form ore deposits. And this is from Ernst 27. You can see that the bushveld is one of the examples. These are all lips events that are associated with economic deposits. In our case, in the bushveld, we have the platinum group rich bushveld and the copper rich Palaboro. So with the platinum group elements, you have the palladium group and the iridium group. This is based on their chemical properties. They concentrate in more mafic and ultramafic igneous rocks. So in this study, investigation, we focused on the clip-rufus-back basalts. We did not analyze the Plattback and the Allen Ridge. And these PGEs are mostly hosted in sulfides. Other people have proposed that they don't have to be analyzed, they don't have to be hosted in sulfides in the mantle. And they can be useful in understanding the mantle source, analyzing the rocks and knowing where the source. You can say something about the nature of the source in terms of the PGE. The concentration of the PGE in the rocks depends on the nature of the source. If it's depleted or enriched, the degree of partial melting of the source, and also saturation of sulfur during the ascent of the magmas. If the magma is saturated with sulfur, the PGEs will partition into the sulfide, immiscible sulfide, and also form these ore deposits. And this can be shown using sulfur isotopes. That's why we also analyzed multiple sulfur isotopes for the clip-rufus-back lavas. So with the clip-rufus-back group or the LIP, we do have the Western Oil Comatiates. And what has been noticed is that the early Archean comatiates are relatively depleted in PGE compared to the late Archean comatiates and the younger comatiates. And these people say that there was change in the mantle PGE through the Archean. There was mixing at the end of the Archean, or some untapped zones were being now sourced that were rich in PGE. And Maya et al. 23 analyzed the Western Oil comatiates for their PGE and compared them to the comatiates which formed in the early Archean. However, these two different comatiates have similar PGE concentrations. So they don't show that evolution of PGE, mantle PGE through the Archean. So the Archean mantle has been characterized to be PGE depleted, or again, there was uneven PGE distribution within the mantle, or during the formation of these comatiates, there was retention of sulfides in the source. So that's the Archean mantle. Moving into the Ventersdorp and also the clip-rufus-back, we don't have any non-magmatic deposits, economic deposits. However, there is the gold at the VCR, and also there's some lead zinc deposits within the Allen Ridge Formation, which are secondary deposits. So we have the comatiates and the basalts of the clip. So this presented an opportunity for us to study the fractionation of the PGEs between the comatiates and the basalts. We looked at the thin sections, looking for sulfides, and we did not find any primary sulfides. However, most sulfides that we identified were associated with secondary features, such as here the vein and amygdals. You can see we have CF pyrite, chalcopyrite, but within secondary features. So within the rocks, excluding secondary, we did not find any primary sulfides. Okay, for the PGE chemistry, on this left side, I plotted the palladium group. This side, I plotted the iridium group. And we see that Western area is relatively enriched in the iridium PGEs compared to the rest of the clip that forms a cluster. And for the palladium group, we see that Western area is relatively depleted, or the rest of the clip, the basalts, are more enriched compared to the Western area comatites. And what you also notice that there is enrichment of these palladium group PGEs with stratigraphy, where the albertine that are at the base on top of the Western area have relatively lower concentrations compared to the Lorraine Edenville basalts that occur at the top of the sequence. So you see the difference in the behavior of the two groups of the PGEs, the palladium and the iridium group. And we also plotted the palladium against copper, iridium against copper. And we see what we noticed earlier in the previous slide is that there's an increase in the concentration of the palladium PGE group with height, with the Western area at the base, Albertine, Orkney, Janet, and Lauren Edenville. We see what we observed earlier on again with iridium, where the Western area are more enriched compared to the basalts. The Western area comatites here have more copper concentrations compared to the basalts of the clippy prospect. So we took the PGEs and normalized them primitive mantle using the primitive mantle composition. So what we notice is that there's this grouping again between the Western area comatites and the away from the basalts. So however, generally they have positive inclined patterns, both of them, with the Western area being relatively gentle compared to the basalts. We see negative iridiums, iridium anomalies, negative gold anomalies. And these red crosses here, this is data from Maya et al. 23, and we see that our data does agree with this data. We also analyze these samples for sulfur isotopes, delta 33, 34, and 36. And the Western area comatiates have the most negative delta 33 as well as 36. Or with the 36, they have a broad range that could also be influenced by alteration. And also probably there's a different degrees of alteration within the sequence of the clip refers back clip. With that PGE chemistry, we have noted that the clip refers back group is PGE depleted. That can be explained by a PGE depleted mantle source or sulfide rotation during the formation of the magmas in the source, or segregation of sulfides, immiscible sulfide liquids during the ascent of the magmas. So we will look into those three possibilities. However, on this plot, we see that the western area has some of the most high copper over palladium ratios. And to form these high ratios, you will need to segregate sulfide from the source, from the magma, because of the differences between the copper and the palladium partition coefficients for the sulfides. And what we notice here with the western area, we know that these are high magnesium lava rocks or products, and you needed high temperature to produce them, and the high degree partial melting. So that high degree partial melting would have partially melted the sulfides within the source. And based on that, we wouldn't say that there was any retention of sulfides within the source. That will leave us with a PGE depleted source or segregation of sulfides during the ascent of the magmas. And also the other thing with that we see is that the primitive mantle-normalized PGE patterns, you had the gentle western area komatiite compared to the steep inclined basalts. That could also indicate differences in degrees of partial melting, where the high degree partial melting of western area was able did partially melt the sulfides, producing that the flat pattern or gentle pattern compared to the basalts, where during the formation of the basalts there was retention of sulfides possibly, enriching the basalts in the light palladium PGE compared to the heavy iridium PGEs. So right now we're gonna have to analyze or assess the sulfide segregation model to see if what we are seeing, is it because of sulfide removal or the source was just depleted in PGEs. One of the ways to saturate the magma with sulfur is to contaminate the magmas. So you need external sulfur. Hence we did the sulfur isotopes, analyze sulfur isotopes. However, what we notice with the sulfur isotopes is that they have these signatures that are referred to as mass-independent fractionated sulfur compositions. These are non-zero delta 36 and delta 33, which were produced during which were produced at the surface when the atmosphere was poor in oxygen. So we find these sulfur isotopes or compositions that originate at the surface, but however, we find them in mantle products. So we have to ask ourselves, why are we having this surface sulfur compositions in mantle compositions products? And one way of explaining this is, the easy way is to attribute them to hydrothermal alteration. And we did see evidence of alteration after the emplacement of the Khulekani spec or the Ventersdorp supergroup. We had fluids that were coming from that past sedimentary rocks transfer or that percolated through the Wits sequence that have introduced these surface sulfur isotopes into the Khulekani spec LIP. Or another way is that there was assimilation of crustal components by the magmas of the Khulekani spec. Another explanation is that in the source, the source was influenced or assimilated a subducted slab that was carrying these signatures. So we know that the rocks are altered, so it's easy to explain using alteration. And again, sulfur is also readily modified by fluids. So for the post-emplacement and alteration, we can say that there was alteration. The fluids that brought in these smooth species into the clip reverse-back sequence, either from the Wits or from the transfer supergroup. And on this plot, I've plotted from literature, taking literature data for the transfer supergroup, the Wits supergroup, as well the Ventersdorp contact reef sulfur isotopes from the literature. We see that our non-zero compositions, they do plot close to the VCR, which is also influenced by the Wits supergroup. So you can easily attribute these smooth compositions to hydrothermal alteration. And also, what we have shown in this study is that based on the niobium anomalies, negative niobium anomalies, we can say there was some influence of subduction in the clip reverse-back, but we cannot ignore the alteration and say that was the cause of the these sulfur compositions. We also saw that the clip reverse-back lavas were not altered, or there was no isotope exchange, well, based on the oxygen isotopes, and also oxygen was an in situ compared to the sulfur, which is a whole rock composition. And we're not able to show any significant contamination of these magmas using the neodymium hafnium isotopes. And also definitely we did not show any contamination based using the oxygen isotope compositions. So we're only left with alteration to explain these mass independent compositions of sulfur isotopes. So in conclusion, for the whole 3 investigation studies, is that to constrain the mantle composition of the source is that we know that the mantle was depleted in composition for the hafnium and neodymium, and there was insignificant crust-down contamination of these magmas. Looking into the whole Ventersdorp supergroup, the clip blood basalt, the silicic blood-back lip, and the null sequence, we now know that there's 3 large igneous provinces in the Ventersdorp supergroup, which is the clip lip, the blood-back slip, and the Allen Ridge lip. And this study emphasizes the effects of alteration and metamorphism on the strontium system, and also the significance of the robust hafnium system, which also points to the benefits of using multiple systems that get modified differently when you're dealing with altered samples. And the clip reverse-back clip has low PGE content and the mass-independent sulfur isotope signatures that are attributed to secondary processes, not to primary composition. We show that the depleted sublithospheric mantle of the clip reverse-back was poor in PGE. And just the last statement again is a repetition, is that this study demonstrates the importance and the value of multi-source data when dealing with altered geological samples. So as analyzing the strontium, neodymium, hafnium together with the oxygen isotopes in situ, the PGE, the sulfur isotopes, were able to constrain the source of these lips. Thank you.
Thank you very much, KK. Any questions? No?
I was just curious if you could sum up for us why the mining PGEs in the bushcraft. What's the difference between the two?
Well, that's a good question, because there's also this debate about the mass balance of the bushveld, about why you have so much of PGEs in the bushveld, whereas other lips they don't have any mineralization. Yeah, but at different times. One of the reasons why we analyzed the sulfur isotopes is that we are wondering if the bushveld did scavenge PGE or deposits subsurface of the Ventersdorp. That's why we have so much PGE within the bushveld. That could mean that the bushveld, the PGE in the bushveld, is not directly from its source. It could have taken up some of deposits on its way to the surface, or when it was in place as an intrusion.
So you have shadow.
Lauren, my best guess would be the crust, because we didn't analyze the plumbing system of the Ventersdorp. We don't know if was it really enriched in PGEs or not.
Grant?
Yeah, well done, KK. Great job. I was going to ask you about your oxygen and cloud pyroxene data, which shows overlap with mantle. But the issue is that the SCLM overlaps with the mantle and all of that, right? So could some of the SCLM signatures in the western area be hidden by the fact that it just happens to overlap with mantle?
Yes, but the narrow range that we noticed compared to the wide range of the SCLM, we're expecting, if our rocks were sourced from the SCLM, we're expecting to see a similar range as the SCLM. However, that narrow range that we measured overlapping with or coinciding with the mantle CPX, we favored the sublithospheric compared to subcontinental mantle.
Thank you.
Scott?
Yeah, I guess my question is the same as kind of what Patricia was asking as well, but what's your tectonic model? You know, like if you have to draw a really simple cartoon, right? You potentially have 3 lips within 80 million years. 3 separate lips. Well, yeah. I don't know, but another example of that elsewhere in the world is, what's your super simple cartoon model for this?
Well, the existing one, I'll tell you about the existing one, is that there was the emplacement of the triple-prospect basalts during an extinction tectonic setting. And then there was a break in the formation. And then later, at least 40 million years apart, there was the formation of the flatback. That was during formation of gradients faulting within this area, where you formed isolated gradients, where you find different flatback sequences. And then there's another break between the flatback and the Nile, well, evident with the unconformities that exist, where you later bring in the Allen Ridge. And also what we see that there's a break because after the Klippel-Perspeck sequence, the flat sequence, at the start of the Bloodberg, you have the Camel Dons formation, which is clastic sedimentary, before you get the felsic Marquas and Rietgat, and also between the Bloodberg, just after the Bloodberg, before the emplacement of the Allen Ridge, there's the Waterville sedimentary formation. So that shows that there was some pause in the emplacement, erosion forming the sedimentary formations before you could start another magmatic event. So that's how you can explain it.
Yeah, I think the key thing is the timescale. It's like 80, 90 million years. So is it continuous across that timescale, or is it punctuated?
Yeah.
I don't know of too many places globally where you have a succession between a sort of well-preserved succession like this with multiple kind of events that could be analyzed. So maybe this is the norm for sort of Neo-Archean, is that you have punctuated lips, multiple lips in a short duration of time on a big scale.
Could it be one fluke, just with some tectonics like graph information superimposed on top of it? You have one fluke, one heat source, but you have superimposed tectonics, drifting and
Over the 70 million. Yeah, that's possible, but I don't want to touch on the multiple theory.
I think that answers Trisha's question online as well, so I won't read that out. So time for one last question before we wrap up. Yes, Trisha says that answers her question. Okay, thank you very much, Keiko, for a great talk.